Hello, let's talk paleodepth. So, the fancy word for figuring out what the depth used to be based on geology or just in general is bathymetry. Um, Bathymetry, and it means measurement of depth, basically. And so, there are a lot of ways you can actually do this. Some ways are easier to do just standing next to a hill. You can say, yeah, deep, shallow, whatever. Some ways require a bit of lab work, but there are, a number of principles, and ideally, all these things will converge on the same answer. You'll find animals that live in the deep water, and here's our anglerfish. That's our little mascot for today. Isn't it adorable? Yeah. I think that's the beautiful lady, and I think those are her little eyeballs up there. I wish they'd shown the little dangly part up here. It may not have preserved on that specimen. Um, yeah. But you should have deep water animals in deep water type of rock, and it should have deep water chemical signatures in there as well if it was really deep water. So you should have multiple sort of independent lines that you can investigate and should all give you more or less the same answer. Yeah, so let's go. All right, shown over here. These are the geological ways. And honestly, you'd have to take a geology course, go out and look at a bunch of rocks. But there are going to be particular things you can recognize. So cross bedding is going to be where you get sort of different angles of the rock. And stuff like that is going to be common in, for example, like a river delta. And so you'll have particular characteristics of the rock that will look like sort of deep marine. You'll have particular kinds of rock that form at the bottom of an ocean, which are different than the kinds of rock that form at the bottom of a lake, and stuff like that. And so geologists can estimate by looking at a formation and doing some simple tests on it back at the lab the paleo depth of that formation. And so that's helpful. There are also, of course, different animals, like anglerfish. You will not find them in your tide pool, most likely, because those are a very deep water fish, and they're specialized for that particular ecosystem. They could get washed up there, like in a storm occasionally, but usually they'll be dead once they do get there. And so, it's you'll find the greatest concentration of these creatures where they live. And so, for certain types of fossils, there are going to be particular depth zones. And so if you have polychaete worms, you can say, okay, we're probably 3 to 65 meters deep, that kind of ballpark. But if you also have crinoids there, you can say, we're probably in the 3 to 25 zone, because in fossils, like in the old times, crinoids were mostly a shallow, lagoon species. So they're behind the reef, which is blocking the big waves, and they're just in sort of the muddy area that gets a lot of nutrients. It has a lot of photosynthetic little creatures in it, and they just prey on those. They're filter feeding, catching all sorts of things, and shoving them down to their mouth. That's how they work. All right. In addition to this, you can have actual sort of scientific methods. So here are several ways. So iron to cobalt ratio. If you're near the shore and there's a lot of oxygen, the iron is going to precipitate, the cobalt is going to stay in the water. So if the rock is made with a lot of iron relative to the cobalt, and you have to compare these to whatever is normal for, for the Earth or for a particular time, then that's going to indicate shallower water. Yeah, and if a higher cobalt relative to this, then it's going to indicate deeper water. This would work very nicely if you have a single formation, like a particular kind of rock from a particular time and place, but you have a change in depth. Like the polar ice caps melted, the water got much deeper for a while and then gradually went shallower, and you have all these layers that are laid down during that succession. That's one way that you can tell. And iron to manganese ratio, thorium to uranium ratio. And again, these are going to be oxidized differently, and you'll have more oxygen in closer to the shore and in the surface, because the more stirring around, like what waves would do, the more oxygen. and you'll only get the waves really on the top. So deeper down, you have lower oxygen levels, definitely. And those will react with different elements. And so, yeah, compare the ratios of these different elements. And that can tell you if you're in deeper water or shallower water, or more oxygenated water, less oxygenated water. And it can help you figure out what is the environment your particular fossil liked to live in. All right, then there are isotope abundances. There are different amounts of some of these isotopes that you find in certain places, like carbon. You can see it's mostly carbon-12, 98%, but there's a little bit of carbon-13. And there are some organisms that are very good at separating out, like they will preferentially take in carbon-12 over carbon-13. And so if you have an abundance of those, then you'll have a lot of carbon-13 left over, which may form the rock. Or if you have a fossil of one of these, you may have a lot of extra carbon-12 in there. And those are going to be very stable isotopes, but they can tell you roughly what it is that actually made that particular formation. And so here is one carbon isotope trace analysis. Yeah, let's move that over a little bit. There we go. Yeah. And so this is showing that you have, like in a brachiopod, look, you have these numbers 5 and 6. This is the ratio of carbon isotopes. And you have really small oxygen numbers, very close to 0. But in the corals that are found in the same environment, those are going to have photosynthetic symbionts in them. And so photosynthesis is one of these processes. Plants are very good at separating out different isotopes of the same atom. Like they can pick out the carbon-12 and as opposed to the carbon-13, for example. And also pick out, you'll have different oxygen isotopes depending on temperature, global temperature in particular. And so, yeah, you get differences in carbon, even though they're right at the same spot and they're both made of carbon. Calcium carbonate predominantly. All right, which all brings us to a sort of a big geological concept, which is the cyclothem. And if we're out fossil hunting, this is a thing that we can sometimes see right on the side of the hill. A cyclothem is cyclical, so it's something that goes around. It's like a cycle, and it's a cycle of changes in depth. And the changes in depth are probably going to be driven by, like you can imagine continents getting lifted up and dropping down. Sometimes that happens with tectonics, with stuff like earthquakes. But more likely, at least in the times where we are examining, like Paleozoic times, particularly around the Permian and Carboniferous, this is a time when the Earth was pretty cool, at least in the Carboniferous, but it was right at that line where if it went just a little bit cooler, you get massive polar ice caps building up. And if it went just a little bit warmer, you would get all those ice caps just melting and dumping fresh water in and raising up the water levels. And the Earth has a little wobble as it rotates around the sun. And it wobbles in such a way that about every 400,000 years, it will have a cycle. And it'll be warmer every 400,000 years, and then it'll be colder every 400,000 years. And so there's about a 400,000 year periodicity, and that's what these cyclothem cycles actually show. It's kind of like they call it a digital chronology. It's like if you can count 3 cyclothems, then it's 3 times 400,000 years, approximately. 1.2 million years. Bam, right there in the rock. Really neat, yeah. You can recognize the different types of rock in these features. The deepest water rock that you will find is going to be called the core shale. It's going to be this black shale. It's going to break into little squares, little hexagons, little tiny things. It's made of super fine-grained material. Because larger rocks, generally, they're going to come from the land. Rocks come from the land. This is what erosion is. And they're probably not going to get pushed very far out. So they'll end up, maybe they don't even make it to the beach. Smaller rocks, like sand, get pushed out just about far enough to get to the beach, and that's as far as they can go, because they're kind of heavy for water to carry along unless it's really rushing off the land. And then smaller grains than that get deposited further out. And so a grain will be carried along in a river current farther the smaller it is. And out over the center of the ocean, like somewhere like the Gulf of Mexico, you get only extremely fine particles gently raining down, almost atomic size. And these things are what's going to make up the rock layers that are forming at the bottom of that. You can look at a rock and you can tell based on the size of the individual grains making up that sedimentary rock, you can get a pretty good idea for how far this thing was deposited from shore. Yeah, which is kind of a proxy for how deep it is, because you're shallow by the shore and then it goes deep everywhere in the world. And so by comparing modern sediments to fossil sediments, we can say, all right, if this was a modern sediment, this would be laid down at about 250 feet of depth or deeper. You can actually use that also to kind of determine your fossil, the depth at which your fossil organism lived. So, if you go through West Virginia, Kentucky, Pennsylvania, anywhere that has mountains of sedimentary rock, a lot of the Rockies are igneous rock, and so that doesn't count. Yeah. But even like some parts of Colorado, New Mexico, if you're driving out there, you'll have these big stripes in the cliff. And sometimes you'll see it'll go like black and then white and then a bit of brown and then black again and then white and then a bit of brown, then black again and then white, big chunky white. These are the cycles. This is probably one complete cycle. So this is when it's really shallow. This is coal, which is from the swamp. So if you were to get up close to that, you'd see it just looks like leaves and stems. It's coal. And then here's some limestone we're depositing as we're getting a little bit deeper. Limestone comes in sort of middle depth to very deep water. And then we've got probably a core shale. This is this little black shale here, which would be very fine sort of powder. And then now that we're all deep, we're going to get shallower. And so here we're laying down a little bit of limestone. I don't know why we're not laying down as much. But when you're farther from shore, you're less likely to get particles coming out there. And if the particles don't come out, they don't get deposited. And if they don't get deposited, they don't form the rock. That's the rules. Yeah. And anyway, here we are. And we're back in near shore. So this is the same point geographically. But it is in shallow water, and then it is in deep water. And it's not that the land is changing, right? It's that more water is present because the polar ice caps melted, and so now it's underwater. And then the polar ice caps reform, and so now it's on land, it's just in the swamp, and they melt again, and they reform again. Yeah. So you got maybe a little over 1 million years on this hillside right there. And you can read it just like a book. Just like a book. Here's a little cyclothem from Texas. Why not? This is in the upper part of the Placid Shale, and it's a nice little cycle. So down here, there's 3 little bands of limestone. Here's a bit of the third one, second one, first one. And these are in shallow water, but it's starting to get deeper. And then just on top of this, you have a kind of a dissolved limestone structure, these sort of orange little nodules. Means there was a limestone there, but it didn't form right, or it got dissolved a little bit afterward. It might have been a bit acidic down there. And then after that, it gets really deep, and the deepest part comes right about here. So that's the blackest part on that hill. And then it starts to get shallower. And you find tons of corals and shallow water creatures here as it's starting to get deeper. And then you get a couple of brachiopods that were fine in the middle depth to fairly deep water. The deepest part, you get nothing because there's very little that lives down there because there's very little energy input down there. There's no sunlight, so there's no photosynthesis. And so you're reliant on dead things falling from above. And there's just, they don't always get to you. A lot of dead things get eaten above as well. That's where all the action is. As we get shallower, we start to get things like snails coming in. A couple of deep water crinoids come in. And then when we get up to here, bam, this shelf right up here, we are now fairly shallow again, and the corals come back. Because the corals, these probably have a photosynthetic partner inside them, and so they needed shallow water in order to be able to basically live, make their skeletons and have enough oxygen to breathe. And so, you get corals here, and you get the deepest point right about there. There you go. that is a little, a cyclothem written in the side of a hill. All right. So, what are some geochemical markers of depth? Things like iron-cobalt ratio, thorium, uranium, I think, ratio. Look back on that other slide. There are a bunch of different ratios that you can take, each of which is subtly different, but a lot of which can be done by a good geochemist. What information is contained in oxygen isotopes? That one is going to be depth. One is going to be global temperature. Yeah, sorry, lost my brain there for a second. Because the lighter oxygen, so there's water. There's water that has oxygen 16, and there's water that has oxygen 18. The O16 water is more likely to evaporate because it's lighter. Yeah, those atoms make a difference. The 2 extra neutrons are holding that other one down. So mostly what you get in the clouds is going to be water with oxygen 16. And then when that, snows and sits on the ice cap and just builds up year after year, that's mostly going to be O16 water there, which means that all the water in the ocean is going to be more O18 because we're losing some of the O16 from there. O18 is always rare. And so you can tell how big the ice caps were, which tells you what the paleo temperature was based on the amount ratio of oxygen isotopes in the rock that were deposited underneath the water. It shows you what's left. And if it's, the amount you would expect for, like all the O16 to be in the oceans, then you can say, oh, yeah, ice caps were probably pretty nearly completely melted. And you could also go onto the land and you could do some other tests and look there. But yeah, it's another way of corroborating depth. What carbon isotopes do we find in corals? I think the important thing is that we find different carbon isotopes. They tend to be the lighter ones because those atoms are being selected by rubisco, which is the enzyme that helps plants grab carbon dioxide and rip it apart and turn the carbon into sugar and get rid of that oxygen gas stuff. Nobody wants that. Plants don't want it anyway. What is a cyclothem and what does it show? It is a cyclic change in depth that shows generally when water levels have risen and fallen in a particular place. So it's like a water meter, and it is going to be accompanied by changes in all the animals and plants that live there, because take something like us that does fine on the land. If you put us under 50 feet of water, we're not doing so great. Yeah. And it's like that for most everything. Yeah. Even marine creatures. They just do not do well at the wrong depth. How can you estimate depth? By looking at a formation. You can look for those little bands. Look for the stripes that make up the cyclothem. Look for that core shale, the core black shale. Look for coal layers, which are only going to be found in very shallow, sort of swampy water, like the bayous, basically. What's the significance of black shale beds? Why, it's going to be, those are the deepest points. Those little black shales that break into little sort of square and polygonal pieces. Those are, going to mark the deepest point. And at the deepest point, you probably find nothing. But above it and below it, and that's a place where you're going to look. And if you get shallow enough, then you'll start to see plants again, like, big land plants. And somewhere in the middle, maybe that's where you find brachiopods. Maybe if you're looking for dinosaurs, you have to get all the way up past the plants, and that's where you start to find their bones, if they're land dinosaurs. So you can tell from these little, if you can read depth, just like by looking at a hill, at least approximately, it gives you a much better idea for where to look for particular fossils. Yeah, because they are very much determined by the depth that was there at the time they were laid down. So yeah, changes in depth that are cyclical, caused by polar ice cap melting. There you go. Cyclothems. All right, that's been Paleodepth. I hope that helps. There's a whole lot more to the study of this, but honestly, that is mostly what I would consider geology. I just wanted to make sure we brought some of the concepts to you so you can see a little bit of how it's done, and then the actual details to be able to do it yourself, that's an extra thing. That's beyond what we're doing here. It's outside the scope of this class. Okay, thanks very much.